At Seco Environmental, we're proud to be your single source for pollution control. It's our mission to protect our shared environment, and we relentlessly pursue that goal by providing reliable products and services to tackle your environmental challenges. Purchasing pollution control equipment can be a complicated process, particularly when you have a system that requires many different pieces of equipment. However, our vast range of technologies and solutions for pollution control and product recovery can eliminate that complexity, lowering your total cost of ownership without sacrificing performance. Across a wide variety of industries, Seco helps ensure you achieve real results. No matter your need, Seco has you covered. Simplify your environmental initiatives with our Seco Environmental family of industrial solutions brands. Seco Environmental is a global leader in air quality and fluid handling, serving the energy, industrial, and other niche markets. Through innovative technology and application expertise, Seco helps you grow your business with safe, clean, and more efficient solutions that help protect our shared environment. We work tirelessly to improve air quality, optimize the energy value chain, and provide custom-engineered solutions for applications including oil and gas, power generation, water and wastewater, battery production, polysilicon fabrication, chemical and petrochemical processing, and more. To learn more, visit secoenviro.com today.
Welcome, and thank you for joining us today for the Seco Certified Continuing Education Series. Today, we will be learning about wet scrubber basics presented by Seco Environmental. My name is Mary Rusnak, and I'm the Marketing Manager for the Industrial Air and Fluid Solutions segment of Seco. With me today are my Seco teammates, Jared Wilkin, Key Account Manager, and Craig Brackman, Applications Engineer. While we wait for everyone to join, I'd like to go over some basic housekeeping items about our webinar platform, as well as the PDH certification. Now, with this first screen here, obviously if you're having sound issues, you won't be hearing me, but hopefully this slide here will help you out. But take a look in the bottom widgets that you see, check your media player, make sure that you're not muted. There's also the help widget with the question mark, that will help you as well. And then if all else fails, go to log out and log back in. You can use the same link that you used from your email. At the bottom of your screen are multiple application engagement tools, or what I call widgets, that you can use. All the engagement tools are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can expand your slide area or maximize it to the full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A engagement tool. Keep ourselves on track. All the questions will be held until the end of the presentation, but you can submit your question at any time. If we don't get to your question live, don't worry about it. We will get to you later. We contact a lot of times after the presentation is over, so definitely send your Q&As over at any point in time. A copy of today's slide deck and additional help materials are available in the resource list. We encourage you to download any resources or links that you might find useful. Also, over on the left-hand side, you're going to notice that we have links to LinkedIn, Facebook, and YouTube. We post all our events live on LinkedIn, or we post all of our events on LinkedIn and Facebook. So if you follow us, you'll be able to know about all the events in the future. The wet scrubber summary would be a useful reference for anyone who's taken the PDH quiz. So I'm going to pause here for a second so you guys can all get that hint. The Professional Development Hour, or PDH, state information is also listed there. Right now, we are able to offer credits in 36 states. Any of the widgets, if you hover over them, it'll tell you what they are. So there's some different things you can do, like share via social, you can email us direct, whatever it is that you want to do, take a look over them. If you look at the check mark widget, you'll see that that will take you to secocertified.com, where you can sign up for additional events or find the on-demand archive. We have 3 more events that are happening this year. Pumps in Thermal Fluid Systems on October 14th, Thermal Oxidizer Basics on October 28th, and then Industrial Ventilation Design on November 18th. And then finally, for all of you that are taking the PDH portion and need the credits, those last two widgets on the end are going to be important for you. They are the test and tracker widget. Obviously, the test widget, that's where you're going to take your quiz. The tracker widget is where it's going to tell you if you have fulfilled the requirements, both the 50 minutes as well as completing all the questions. Once you have fulfilled all the requirements, you go back to that tracker widget and you will be able to print out a certificate. So a couple of other things here. Webinars are very bandwidth intensive, so make sure you close out any unnecessary browser tabs. It's going to help you with conserving your bandwidth. Some networks also cause the slides to advance more slowly than others, so log off of your VPN if you can. If your slides are behind, pushing F5 on your keyboard will refresh the page. I've also found that Chrome seems to be the best browser for this platform. You can find additional answers to these technical issues, again, on that little question mark widget at the bottom, the help tool. An on-demand version of the webcast will be available after the event and can be accessed using the same audience link that was sent to you earlier. All of the interactivity remains, including the testing capabilities, so definitely feel free to use that at any point in time. So for the PDH portion today, today's webinar is worth 1 professional development hour. You must be present for at least 50 minutes. That's both for if you're on the live version or the on-demand version. If you get interrupted or need to leave or have any other type of issue, you can come back to the on-demand version and complete all the requirements. You must complete and pass the test at the end, which is basically 8 out of 10 questions. Once you have fulfilled all these demands and requirements, you will actually be able to print out the certificate directly from that one widget. If you don't have the time to print out that widget today, you can always come back and print it out at a later time, or if you should happen to lose it. We will keep the records for 6 years, and if you have any questions or any issues, feel free to email me at any time. This webinar is 1 hour long, but we will keep the platform open for an additional 30 minutes after the event to allow completion of the quiz and printing of any materials. So just a little bit here before we move on. This is just a basic outline of what it is we're going to cover today. This is definitely a basic overview of wet scrubbers, and we're just going to hit a couple of these different sections here. And hopefully there's going to be enough information here for everyone who already knows about wet scrubbers, as well as those who maybe just are new to the industry and don't quite understand it. Lots of interesting things here, as well as going through design considerations. And then at the end, we're going to actually take a look at some examples to show you how the scrubbers are used in different applications. But before we get started, we're going to start with a poll question, and you will be able to answer the question on the next slide. So, how much experience do you have with scrubbers? I'm an expert, I have some experience, I have a little experience. What is a scrubber? And here's where you can answer the question. And we'll give you a couple seconds. All right. All right, so we have a good portion in here that have some experience and have a little experience. We got a wide range. I think this will definitely help. The presentation will help most people here. Might be a little bit basic for some of the experts, but I think there's still a lot in there that you're going to be able to pick up on this. And we're now going to move on into the presentation, and I'm going to pass this off to Jared.
Thank you, Mary. Hello. I'd like to start off our journey into the world of wet scrubbers with focus first on the airstream, or exhaust flow, by defining what we are looking for and why. One of the most common applications we see a wet scrubber utilized in is acidic gases and mist, such as nitric, HCl, and HF. So we'll start with this group we classify as hazardous air pollutants, or HAPs. Other examples of these contaminants in this group are ammonia, SO2, and H2S. In general, HAPs are hydrophilic in nature, water-soluble, and can be wet scrubbed. Moving through the airstream to the next species is volatile organic compounds, or VOCs. Some examples of these are ethanol, acetone, methanol. These are a less common application, but can be used as a once-through water system. This is costly for wet scrubbing and usually not the most efficient. Just as oil does not mix with water, this is not the best application. We can find more energy efficiency and better destruction removal efficiency, or DRE, with thermal oxidation. In general, VOCs are hydrophobic in nature, non-water soluble, and cannot be wet scrubbed. Particulate matter. Finally, our last and one of the most frequent culprits in our airstream is particulate matter. We can see the definition above, and in most cases we group this into two categories, 2.5 and 10 ppm. While wet scrubbing can handle these emissions, it is not the most efficient in handling these contaminants. If your airstream has particulate matter and acid gases, this might require a system train of air pollution control equipment that entails separation of particulate matter before wet scrubbing acid gases. If you would like to learn more about particulate matter and how that can be collected via Venturi Cyclone or Dust Collector, please sign on to CECO Certified to look into the cyclone fundamentals. Wet scrubber definition. Now that we have an idea of our airstream and our main players, we need to start with some basics, like a definition of a scrubber. A packed bed scrubber, also referred to as a wet packed bed scrubber, is an air pollution control device used to remove and destroy contaminants in an air gas stream. To simplify, imagine a large vessel or container, like a big propane tank turned on its side, that is empty except for something that resembles baseball wiffle balls inside, held in the center, with a shower head at the top running inside with water, collecting at the bottom like a bathtub, that is cleaning dirty air, which collects dirty water at the bottom of our vessel, just like when we shower. Scrubber definitions. We will discuss a little later how a scrubber removes air pollutants, but for now, it's important to know that scrubbers are capable of removing inorganic fumes, vapors, gases, and mists. A scrubber can be used for particulate matter control, but higher PM concentrations can clog the scrubber internals. So a scrubber is limited to airstreams with low dust loadings. If you have an application for high particulate matter, CECO has another equipment solutions for that application. See CECO webinar. Bottom line, scrubbers are not vacuum cleaners. Reasons to use a wet scrubber. All the reasons above are true for the use of a wet scrubber, but the main driver is human capital, physical capital, and environmental standards. Number one, the area in which workers are present does not have adequate air quality standards. Number two, the process is so corrosive or dangerous, the air fumes must be evacuated and removed for the health and safety of the equipment and facility. And lastly, the end user is under state, local, or federal ordinances to require APC equipment or an air permit. Wet scrubbing process. Wet scrubbing is a two-step process. In the first part of this process, we are simply trying to capture the contaminated air. I think a great way to connect this is think about allergies. Anybody suffer from pesky pollen? Nothing helps more than a nice rain, and the proof is in the water. If you've ever watched runoff water after a rain event, you may see a yellowish hue in the water. That is pollen. All the pollen in the air, we will call dirty air, is then cleaned after a rain event. The contaminant or pollen passes through with the help from mass transfer from air into water. In the second step, we're trying to then break apart these molecules back into clean air and exit the scrubber with no contaminant or scrubbing liquid. Another good example of how this process is achieved is with the mist eliminator. Think about an early morning walk near a garden or forest and seeing a spider web covered in small droplets. These small water droplets are grabbed as it passes through. This is similar in the way that a mist eliminator is able to grab the moisture from the air as it leaves the scrubber. Scrubber types. Before we move deeper into the scrubber process, let's take a step back. You may have heard the word scrubber used for other air pollution control equipment such as bioscrubber, Venturi scrubber, spray tower scrubber, or tray tower scrubber. The best way to distinguish between these different types of scrubbers is best to understand each has a niche application usually associated historically with a specific industry or location. This could be determined in the case of operational costs versus capital costs, or possibly some end users' limits on the amount of fresh water available. Example industries. As for the industries listed above, you can see wet scrubbing has a fit in many processes. Most important when looking into a wet scrubber application, no matter the industry or size of the system desired, is the data. It is pivotal to provide the most current process or stack testing data available. Process examples. This data we are looking for is the following: the CFM, or airstream volume, concentration of contaminants, and required destruction removal efficiency. This allows us to properly size and engineer a system solution that is the most efficient and fits your needs. The most important is understanding what the process is. This will help us determine what type of scrubber system and design will fit best for your application and location-specific parameters. Such as one of the examples above, in wafer chip manufacturing for semiconductor. We usually see a horizontal packed bed scrubber in fiberglass material construction, most commonly rooftop installation, with some special requirements such as redundancy in pumps and fans, which we would not find in metal plating application, for instance.
All right, everybody, we are at our next poll question. And again, like the last one, you will be able to put your answer on the next slide. So what type of wet scrubber are you most familiar with? And for this one, you can actually choose as many as apply. So we have packed bed scrubber, Venturi, spray tower, carbon adsorber, or other. And here's where you can add your information. I'll give you guys a little bit of time on this one since you might have more than one that you're familiar with. Give you a couple more seconds. We'll take a look at the results and see what everyone out there is familiar with. Not too surprising that the packed bed scrubber would be the one that people are most familiar with. It definitely is the one that is seen out there quite a bit, along with the Venturi, but definitely it seems like people have experience across the full spectrum of different types of scrubbers that are out there.
All right, we are now going to start getting into the nitty-gritty of the scrubber discussion. Here on the right, you're looking at an exploded view drawing of a typical vertical tower. There are 5 major components that are normally used in a wet scrubber. They are the packing media, the mist eliminator, the recirculation pump, spray nozzle, and the instrumentation and controls. We'll see in a moment the packing media is the heart of the scrubber. The mist eliminator removes the large droplets. The pump recirculates the scrubbing liquid. The spray nozzles irrigate the packing media with the scrubbing liquid. And the 5th major component, though not shown in the exploded drawing, consists of instrumentation and controls. There are over 20 different items that we can customize a solution for. The minimum basic ones are flow meter, pressure gauges, valves, pH probe, differential pressure gauges, water makeup, and liquid blowdown systems. So let's move on and see how all these components work together. So here's a brief description on the theory of operations of a scrubber. Basically, how does this thing work? The graphic shows a vertical scrubber, and the center of the tower is filled with the packing material. This packing creates large surface areas and multiple drip points for the liquid to come into contact and mix with the contaminated gas stream. The packing is held in place with a support plate, basically a grid material at the bottom of the packing material. And the bottom of the scrubber contains the sump and the scrubbing liquid. And a pump sprays this liquid over the packing media, usually spray nozzles, so it's evenly distributed and flows down the packing media. These can also be done through weir troughs and a few other different methods. In a vertical scrubber, the contaminated gas enters at the bottom of the scrubber, as shown here, and flows up through the packing media. The air contaminants are either absorbed due to their solubility with the scrubbing liquid or chemically reacted with a chemical additive such as sodium hydroxide or sulfuric acid that has been added to the scrubbing liquid based off a pH or an ORP measurement. There's also a third method of treatment of removing air contaminants that we'll discuss at a later date or later point in time in this presentation. The clean gas is now exhausted into atmosphere, but before doing so, it passes through a mist eliminator section. The purpose of the mist eliminator is to capture any small droplets that are blown off the packing and also capture the smaller droplets from the spray nozzle that become airborne. The standard mist eliminator for a vertical scrubber operates at approximately 700 feet per minute and is usually a vane-style mist eliminator that can capture droplets 20 microns and larger that then agglomerate and drain back down into the scrubber system. We'll talk about some other mist elimination options that are a greater removal efficiency later on in the presentation. To put this into perspective, the limit of the visible human eye is about 40 microns. So this is not meant that the clean gas has no moisture. As a matter of fact, the system is super saturated coming out of the scrubber and is roughly 100% humidity. The contaminated gas that was once dirty has now been cleaned, and the scrubbing liquid that was once clean has now contains the air contaminants. So two more points to make before we move on. The scrubbing liquid is usually recirculated, but in some applications it can be done as a once-through water system. And then the second, this is a vertical tower, but towers can also be built in a horizontal direction, known as a cross-flow style design, which we will be discussing. Earlier, we talked about three methods of how air contaminants are absorbed and transferred into scrubbing liquid. An example of the first method is when a chemical air contaminant is absorbed into the scrubbing liquid using water only. When scrubbing is a strong acid like hydrobromic, which is soluble in water, it will ionize, forming a hydronium ion and a bromine ion as shown. Ionization means that the molecule acquires a negative and positive charge and undergoes a chemical change. Likewise, a strong acid such as hydrochloric acid will ionize in scrubber using water only, using a hydronium cation and a chloride anion, and once undergoes the chemical change. There are many chemicals that are soluble in water that can be removed in an airstream using a once-through water only system. The second treatment method that can be used to remove air contaminants, but these can only be removed with the addition of a chemical additive. An example is sulfur dioxide, as shown, reacting with water and a solution of sodium hydroxide at a pH of 9 will produce a sodium sulfite in water. Reactions like this are shown in green that are typical acid-base reactions forming a salt and a water, which has a neutral pH of 7. This reaction occurs in the packed bed section of the scrubber and is called a neutralization reaction. An example of this is if you ate too much spicy food for dinner, you can relieve the stomach acid or the heartburn by taking an antacid tablet. That'll neutralize the stomach acid. In other words, it's a neutralization to ease your heartburn. The second chemical reaction and neutralization shown here is a common contaminant of hydrochloric acid reacting with sodium hydroxide to produce table salt and water. As a side note, you will notice that we had briefly talked about that you could use HCl with water only, but here we're showing you can do it as a chemical reaction. The reason is that in some cases, the addition of sodium hydroxide to the scrubbing liquid actually improves the removal efficiency, which leads to a more efficient scrubbing operation. So you need a pH control. The pH control is optional for hydrochloric acid, but we do use the chemical addition pretty regularly to improve the removal efficiency. The final example of a common air contaminant is ammonia reacting with sulfuric acid to produce soil fertilizer ammonium sulfate. So these all create a fairly soluble salt. I mentioned earlier that there are 3 treatment methods to remove air contaminants in scrubber. This third method is applicable for a large group of chemicals. The standard chemical engineering gas absorption calculation does not apply to these chemicals because these chemicals are not as a gas form, but are present as a mist droplet or a fume. These chemicals are essentially non-volatile. Non-volatile is just a fancy way of saying that these chemicals do not readily evaporate in the gas like the previous chemicals that we had discussed. So you may ask, how do these chemicals get into the airstream in the first place? Well, these acid mist droplets or fumes are mechanically generated and enter the airstream at a process and formed by either splashing or spraying or bubbling gas through tanks containing non-volatile acids and chemicals. We have less than 7 of the common air contaminants that fall into the category of non-volatile chemicals. Scrubbers remove these mist droplets or fumes by mechanical process of impaction rather than absorption. Extensive experience shows that these well-designed scrubbers can remove 99% of mist fume droplets 5-micron range or larger. Now, some of you may be asking, why are you making such a big deal of this third treatment method? Well, in my experience, this third method is probably the least understood and creates some confusion versus the other 2 methods. We'll cover a few major points to help you better understand this method. There's usually an exception to every rule. First, you'll notice that 4 of these chemicals have an asterisk next to them, and it's possible for these chemicals to vaporize if they are heated enough and are used in a hot process at the source. Any of these chemicals listed are being emitted by a hot enough process to actually vaporize them, typically 200 degrees C or higher. Then they will condense into micron or sub-micron sized fog droplets when mixed with a cooler airstream on the way to the scrubber. A scrubber cannot remove these fog droplets and will require high efficiency filter beds such as a candle filter or a CECO filter. It is important to alert and advise any of your scrubber manufacturers if these chemicals are heated at the source, such as a hot plate or even through air temperature, as it may be cooled down to ambient temperatures, and we can put the proper provisions in place. Second, as already mentioned, we cannot provide a calculation for the removal efficiencies of these chemicals. The removal will depend on the droplet size distribution, which is usually not known and easy to measure. Therefore, stating a scrubber can remove 99% of mist or fume droplets is only telling half the story. You'll need to add the statement that a scrubber can remove 99% of the mist or fume droplets 5 micron or larger, or 10 micron or larger, or whatever size mist elimination device is required for the process. Third, there's an exception to this rule for nitric acid. At room temperature, roughly 72 degrees Fahrenheit, nitric acid concentration less than 15% nitric is present in the airstream, and mist droplets, fumes, and the 99% removal of 5 micron or larger rule applies. On the other hand, if the nitric acid source is concentrated or even hotter, some of the nitric acid can vaporize, and then standard chemical engineering absorption calculations now apply to the nitric acid removal. Fourth, these chemicals can be scrubbed efficiently with water alone, and the addition of sodium hydroxide will not impact the removal efficiency. This means the pH of the scrubbing solution has no effect on the removal of these contaminants, and the pH of the scrubbing liquid can be 7 or even lower without affecting the removal of the mist droplets or fumes. Now, there's nothing wrong with adding sodium hydroxide or pH control to maintain your sump liquid at 7 or higher for neutralization purposes. It may make it a little bit easier to treat once the liquid is blown down. But sodium hydroxide has no impact to the removal efficiency of these specific components. Finally, occasionally we see scrubber data showing concentration of 100 ppm of sulfuric acid or nitric acid. This is not possible for the vapors to exist in the concentrations at room temperature, and 100 ppm is obviously incorrect. Mist droplets or fume concentrations should be reported using measurements such as milligrams per cubic meter or grains per cubic feet, and concentrations of volatile chemicals in the vapor phase should be treated as ppmb. So here are a few photos of some mist elimination or filter devices that we can put within a scrubber. The one at the bottom left-hand side is a vane style mist eliminator. So that's a typical Chevron device, which can achieve about 99% of 20 micron. And the photo next to that kind of shows how the droplets zigzag through the Chevron style mist eliminator. The upper left-hand corner shows a mesh pad. This is actually looking down from the top of the mesh pad. The yellow are the grids and the black is the actual mesh pad below it. And then over on the right-hand side, we have a candle filter arrangement, which is even for finer collection. So the Chevron style will get you roughly 20 microns. The mesh pad will get anywhere between 10 and 5 micron, or better for some of the specially engineered mesh pads. And then the filter candle arrangement will even do better than that. All right, so let's get into some configuration. We've covered some heavy technical items. Now let's lighten it up a little bit and briefly talk about scrubber configurations and options. Earlier, we introduced you to vertical scrubbers. And this is a picture that shows a simple vertical scrubber with a side outlet at the top. The outlet can be adjusted to the center of the tower, so it doesn't have to go 90 degrees. It can go straight up in the air. In a vertical tower, the contaminated air enters the bottom of the scrubber and flows upward through the packing media to the outlet. Spray header lines are located above the packing material that deliver the scrubbing solution down on top of the packing and flows down through and drains back into the scrubber sump. In this configuration, air flows up, liquid flows down in a counter-current fashion. They basically pass each other and mingle within the packed bed, which is why this configuration is called a counter-current scrubber. There are two basic designs of a vertical scrubber, as shown in this slide. It can either be a square rectangular or it can be a round shape. We have listed the main benefits and facts for each shape. A square shape makes the most efficient use of the available footprint. The length by width can be adjusted in 1/4 inch or 1/8 inch increments if needed. The design of irrigation system is simplified since we use a square spray nozzle pattern to cover the square of the rectangular area of the surface area of the packed bed. A vertical square scrubber needs to withstand a vacuum of approximately 15 inches, external ribs will need to be added to the actual fabrication process to give it that additional strength. There's a premium cost for a vertical square scrubber since the custom wood molds need to be designed and built so the fiberglass can adhere to the exterior. This mold is typically not recycled. It's removed after the fiberglass cures and then is disposed of. The last three items are basically the reason for the increasing cost from a square or rectangular vertical scrubber versus a round scrubber. On the other hand, a round vertical scrubber is a pretty cost-effective solution since it uses a metal mold that can be hand laid up or chop sprayed or spun around it. Its circular shape also is mechanically stronger compared to the square scrubber of the same size. This means external ribs are not required to withstand the vacuum requirement. Pertinent duct and tank molds are used. The diameter is pretty limited to what's available within the market. Round spray nozzles are used for the liquid irrigation, and there's typically overlap between the spray nozzles to prevent dry spots. Finally, the round versus square scrubber makes less efficient use of the footprint because you don't have an actual square. You're actually using just a portion of what you have through the circle of the tower. A couple slides earlier, we mentioned that a scrubber can also be designed with the gas flowing in a horizontal direction. This graphic shows a horizontal scrubber with the contaminated air entering on the left and then flowing horizontally through the packed bed media and then through the mist eliminator section. Spray headers are located above the packing, and that delivers the scrubbing solution over top of the packing and slows down and drains back into the sump. This configuration, the air flows horizontally, and the scrubbing liquid flows down, and they cross each other, which is why this configuration is commonly known as a cross-flow scrubber. Other than the airflow, both vertical and horizontal scrubbers have the same major components. There are some differences between the two designs, and this may help you decide what suits your specific scrubber needs better. We'll get into some of the differences between the two scrubbers and why you would want to choose a vertical versus a horizontal or vice versa. Some believe that one scrubber configuration is better than the others, but actually each configuration has its own advantages and some disadvantages. Let's start with the vertical tower or the countercurrent configuration on the left. A vertical tower makes efficient use of the footprint and uses less floor space. The countercurrent action of the air traveling up through the scrubbing liquid flowing down usually is an efficient design. Since the air near the top of the scrubber contains the lowest concentration of the contaminant, while a recirculating liquid at the top of the pack bed contains the highest concentration of chemical additive. So you think of the final, look at this as like the final polishing section of the pack bed scrubber. A vertical scrubber is preferred for difficult scrubbing applications because of the long pack bed depth that's required. So you can adjust the height of the scrubber, from a 3-foot pack bed to a 20-foot pack bed if you needed to, and you're still using the same footprint of the floor space. There's no chance of air bypassing if untreated. There are no baffles required for a vertical tower. Although it requires less floor space, a vertical scrubber is taller in height than the identical horizontal scrubber. There are a couple options for fan locations. You basically need a process fan for all these scrubbers. So you can either put an inline fan mounted directly to the top of the scrubber, or you can utilize additional square footage and put the fan next to the scrubber, requiring an interconnecting gooseneck that goes from the scrubber outlet to the fan inlet. Because of the height and the concentrated load on the roof, vertical scrubbers are typically not used in rooftop applications. They can be done, but they're just not very user-friendly. I think you start to see the components of the vertical scrubbers are up in the air. So maintenance access it's not a problem, but it's got to be, you've got to put that into consideration. So you may need a work platform or a mechanical lift. The air entering the scrubber has to make a sudden 90-degree turn before it enters the pack bed. So there's careful design considerations on the height between the gas inlet and the bottom of the pack bed to make sure you have the proper velocity profile. And then number 10, flooding. So flooding of the pack bed section is normally not a concern for these scrubber applications, but it does deserve mentioning. Flooding typically occurs at a very high liquid rate and a high air velocity. So using a standard random dump packing, typically flooding occurs at like 40 GPM per square foot at a velocity of 700 feet per minute. This liquid rate is about 6 times faster than what we would normally put in industry standards, and that typically the airflow rate, we aim for about 500 feet per minute. So the bottom line, flooding of the packing is not necessarily a concern for our designs and most common designs within industry. All right, let's move on to the horizontal scrubber or the cross-flow consideration on the right-hand side. You'll see some clarity on a lot of these items we discussed compared to the vertical configuration. So the horizontal scrubbers are shorter in height, but require a larger footprint. Everything is at ground level, which simplifies the maintenance. So you may just need a little shelf or nothing from a platform standpoint because everything's readily accessible. The fan is typically close coupled and is located at the scrubber outlet. Because of the larger footprint, the scrubber weight is distributed evenly over, or relatively evenly over a large area, not concentrated to one specific section, taking the majority of that load. The above items make the horizontal or low profile design a great candidate for rooftop applications. The air flows through the scrubber in a straight path without needing to make a sharp turn that we discussed in the vertical tower. The droplets that reach the mist eliminator in a horizontal scrubber are typically large and drain back down into the scrubber sump. In the vertical scrubber, the droplets are collected from the mist eliminator and then drain back down through the packing. So that's a slight difference between the two. Some air contaminants require multi-stage considerations for different chemical solutions. So horizontal scrubber is ideal where you can segregate these different chemical arrangements. So you may have one section that requires sodium hydroxide. You may have another section that will require a sodium hypochlorite specific injection. And you can actually segment these sections in 3 to 5 foot different pack beds. The horizontal airflow will push the liquid away from the front face of the packing, especially at higher air velocities. Typically, we would include a front spray to make sure we're utilizing all of the pack bed section and avoid the front face of the pack bed to become dry, or even covered with, if there's some particulate in the airstream, to be covered with dust. Baffles are strategically placed within the horizontal scrubber to eliminate any chance of the air bypass at the top or the bottom of the liquid sump or the spray nozzle area. Just for instance, if even 1% or 2% of the air bypasses the packing section, this would be virtually impossible to even design a 98% removal system with a crossflow system if those baffles are not put in there and you have some level of bypass. So for some applications, like removing 99% of ammonia in the airstream, the operational set point may need to be below 3. 3 is a common pH level for ammonium and sodium and sulfuric acid injection, but the reaction occurs on the inlet side of the packing where the ammonia concentrations are the highest. So since you're distributing it throughout the whole pack bed, you may need to adjust that packing or the pH ratio from like 1.2 to 2. So experience shows, experiences trial and error may be needed to see how low you need to set that in a horizontal scrubber. So in summary, you can see that each configuration has its own advantages and disadvantages. We can design and engineer a vertical or horizontal scrubber to the efficiencies that you need. While it's not impossible to draw a line in the sand, a vertical scrubber is a better solution for a difficult application. And what exactly is a difficult application? It's one with high loading and high removal efficiency. So the most common material of construction for a scrubber wall is fiberglass. Polypropylene and PVC are very close to that, and a lot of scrubber manufacturers can provide any of the materials, and there's some on here that aren't even listed. The graphic to the right shows a fiberglass composition detail of a typical scrubber wall. It's got 4 distinct layers. The first layer on the interior of the scrubber is called the inner corrosion barrier and provides the primary corrosion barrier consisting of a resin-rich layer and a synthetic veil. This can be a Nexus veil or a C veil, and it provides the primary corrosion barrier to the system. The second layer is called the interior corrosion layer, consisting of resin and chop strand glass mat. These first 2 layers together make up the primary corrosion barrier. The third layer is called the structural layer, consisting of resin and glass. The total thickness of this layer is determined by service requirements and the structural requirements of the actual process and the size of the vessel. The fourth and final layer is a top coat, a pigmented layer, which is usually colored in tan or white or some other various color, and it's got a UV inhibitor for outdoor usage. Basically, the bottom line is most scrubber manufacturers can design around your specific needs.
Thank you, Craig. That was great. And we are at our next poll question, and we're actually kind of hitting the home stretch here. So just a few more slides here. But obviously, we just talked about different materials of construction, and we are curious to see what material are you seeing or using most in your wet scrubber applications. And you'll be able to put your answer in the next slide. So FRP, like we talked about a little bit more in the slide before, some type of PVC, polypro, an alloy, or something completely different. And I'll give you all a couple seconds here to put your response in. Give me another second, and we'll take a look and see what everybody out there is using or seeing the most. All right, let's take a look at these results. So definitely FRP is over the top in terms of 52% with the majority of people seeing it, but obviously the other plastic options are in there as well. And then you obviously see in terms of the alloys and some of the more exotic metals that will come into play with certain applications. So not too surprising. Thank you for that. Okay, and we're gonna move on to the rest of the presentation.
So you've got a few more slides here before we start getting into some process examples. Let's talk about some do's and don'ts. Remember earlier when we said that acids react with bases to make salt? Well, when an acid and a base are mixed together in the airstream, they do react to form a salt, which can be a smoke particulate, a very sub-micron fine particulate that'll blow right through the scrubber. Such tiny particles have such low inertia that they won't collide with the packing or they won't get wetted in the airstream. They just don't come in contact with the water, and they just streamline and zigzag right through the packing. So specifically, when an airstream containing ammonia gas also contains an acid like sulfuric acid, it reacts to form ammonium sulfate and ammonium bisulfate salts. The reaction starts in the duct prior to even reaching the scrubber, and the same holds true for other acids like hydrochloric, hydrofluoric, and nitric acid when a base is in the airstream as well. The ductwork leading up to the scrubber will eventually contain large deposits of salt, but some of the salt particles will be discharged in the air as a visible emission. So in the case of ammonia reacting with hydrofluoric acid, the particulate will be ammonium fluoride. We realize that sometimes it's sometimes impossible to isolate the acid and the ammonium bath, but we recommend designing separate exhaust systems with dedicated scrubbers for both of these systems. We've already mentioned that scrubber is not a vacuum, and to avoid exhausting particulate matter into the scrubber. While some scrubbers can handle a small portion of particulates, we definitely don't want to overload it. We want to put a different piece of equipment in the air pollution control train. We recommend installing the pH probe as a submersion installation and not an inline insertion. This will give an improved life, a better reading of performance, and simply the removal of the pH probe to perform regular recalibration will be simpler. Another location is placing the pH probe at the bottom of the packing where the chemical concentration will be the lowest. We suggest injecting a chemical into the scrubber sump and not in line to the recirculation system. This location will allow for proper mixing, and the pump impeller will help provide that mixing prior to the scrubber being sprayed on top of the packing. The injection port should not be close to the pH sensor because you may short circuit that reading and get a false reading and you may not give the system the proper chemical additive that it needs before it's used in the scrubbing liquor. There's a group of air contaminants that will decompose when released in the airstream and react with moisture in the air. The list of these chemicals are on the right, circled in green. It includes a short list of these chemicals. The scrubber can usually remove the acid byproduct, but not the particulate or the smoke particulate that is formed. These compounds are better treated in a burn box with a fabric filter to capture those smoke particulates and then exhausted into a scrubber to remove the acid byproduct. There are a number of choices when it comes to specifying and choosing the correct spray nozzle type and spray nozzle pattern. We recommend against specifying any spiral type spray nozzle designed for most scrubbing applications. This just doesn't give the spray pattern that we would typically see with a full cone or a 60-degree cone design. And finally, we have noticed an interest in recent years in scrubbing and treating fluorine gas. Fluorine, when released into the airstream, reacts with water vapor to form a variety of toxic components. The HF byproduct will be removed with high efficiency within the scrubber, but the other byproducts and any remaining fluorine gas will not be removed through the scrubber. Point-use burn box is recommended, and the exhaust gas can be cooled and then sent into the scrubber to remove the HF product. So let's talk about removing the destructive removal efficiency. How is that calculated for a volatile inorganic compound such as HCl or chlorine gas? Well, it's a simple formula. Z, which equals your overall packed bed, N, which equals the number of transfer units, HTU, which equals the height of the transfer units, and then we throw in a safety factor. Safety factor can be anywhere from 1.1 to 1.2, and that'll help you determine your packed bed height. So let's unpack this a little bit. The NTU, the depth of the packing needed to provide certain removal efficiency, it's a really long, drawn-out equation, but it can get simplified, where it's the natural log of the concentration in versus the concentration out. So in this example, we've got 100 ppm. We want 99% removal, so it'd be natural log 100 divided by 1, which would get you 4.6. So then let's look at the two examples we have on here for a minute and look at the height of the transfer units. The HTU depends on three things: the kind of packing being used. There are many different types of packing that are available in the marketplace right now. The airflow and the liquid rate. Together, all of these items will give you an HTU number. A large HTU number means that a more difficult separation. A smaller HTU means that it's an easier separation. So basically, it's easier to scrub with a lower HTU. It's tougher to scrub with a higher number. HTU is an empirical number. It's based off physical properties of the chemical, done by lab testing, or it's been calculated via field testing. And a lot of the different packing manufacturers have a really good understanding of what you need to achieve, and they're great resources when designing a packed bed. So let's continue to look at these two applications for a 99% removal efficiency using a 1.2 safety factor. So you can see the HCl, which is judging by the low HTU number, is easier to scrub, and you can achieve 99% in about a 4.5. Or we may round it up to a 5-foot packed bed. Now for chlorine, to do the same thing, it's got a slightly higher NTU at 1.19. We're using the 4.6 for 99% removal safety factor, and then that gets us to a 6.56, and we would bump that up to a 7-foot packed bed. So you can see within the two, you're still looking at 99%, but not all chemicals are created the same, and you'll actually have to put a taller packed bed to get the 99% of chlorine. Now, you can still run HCl through it. You're just going to get a greater removal efficiency of HCl. So it may be closer to 99.5 in that scenario. So what factors influence or improve the destruction removal efficiency of a volatile and organic compound? Based on what we just learned, the greater packed bed depth increases the residence time of the air contaminants and improves the removal efficiency. So choosing the right packing, which is the heart of the scrubber, makes all the difference in having a scrubber operate efficiently. When air pollution control devices like scrubbers were first designed, people were chopping up PVC pipe, they were chopping up glass and putting them in a tower, and that was your very crude tower packing. So nowadays, the technology has improved so much back through the 70s all the way to the 90s and to current. They made significant advancements and improvements to allow lower pressure drop, higher operating velocities, improved efficiencies, resistance to fouling, and they're more cost-effective than your traditional like Raschig ring that we've seen in some design books. So I mean, there's a lot of different options, and your local scrubber company or a packing supplier can really help you determine what's the best one. So some of the other options we can do, we can slow the airstream down. That'll improve the residence time, which will remove efficiency. We can increase the recirculation rate. That has a positive impact on removal efficiency, and we'll get to that example here in a second. Most cases, higher temperature and the higher temperature will increase the rate of reaction, which will improve scrubbing efficiency. With packing being the heart of the scrubber, any buildup on the packing surface in a salt or a mineral deposit will change the performance. So you want to keep that clean. If there's buildup, it'll be negative. So you want to increase the blowdown in that case and put more fresh water into the system. That will a cleaner scrubber is a happy scrubber. And if a pH operating set point is maintained per recommendation, increasing the pH or decreasing the pH, depending on what the chemical injection, may not necessarily improve the efficiency. This may just increase, this may result in an increase in wasted chemical consumption and may end up being a maintenance issue. So now you may ask, what is the impact of changing these factors on destructor removal efficiency? So in general, the improvement in the destruction removal efficiency will be logarithmic and not linear. So this is going to be a logarithmic and not linear impact. So if you look at the graph on the right, the red line is a linear, and then the blue line is the actual impact. So the graph shows recirculation rate of a vertical scrubber treating 15 ppm of hydrochloric acid at a pH of 8. So you can see that doubling the recirculation rate from 200 to 400 GPM only changes the DRE from roughly 96.7 to 98.8. This illustrates the point that the improvement in DRE is not linear but logarithmic. This graph also shows that it becomes increasingly more difficult as you get to a higher efficiency as you reach 100%. The curve starts to plateau, and there's a point of diminishing returns. So there's a couple exceptions to the rule that we talked about in the webinar, and we're going to introduce one more of those. In general, strong acids such as hydrochloric acid, nitric acid, bromic acid, sulfuric acid, and perchloric acid tend to form an aerosol at higher concentrations. During tank filling operations and during catastrophic releases. When these acid gases are released at higher rates, much of the acid will condense in water vapor and form submicron particulate or an aerosol fog, which will not be removed efficiently in a packed bed and a standard type mist eliminator. So changing the flow rates or increasing the pH will not have an effect on these small droplets. Experience tells us that removal of all forms of these acid gases will probably fall into the 80 to 90% at high concentrations during these tank filling applications or catastrophic releases, because 10 to 20% of these acid gases get converted into fog and will appear dense white plume. So for HCl, the lowest concentration at which an aerosol plume starts to form, and it's difficult to calculate accurately, will typically be around 20 to 85 ppm. So in this case, for these applications, an engineer may put a high efficiency composite mesh pad or a CECO filter like we had discussed before to get that 99% of 2 micron and larger. So anytime you have a more efficient pad, you will have an increase in pressure drop. So the advantages of wet scrubbing, just as a generality, they are often the most economical form of gas particulate separation. They're simple to operate and maintain. There are very few to no moving parts. You have basically the recirculation pump as the main moving part. They can be designed for severe service design, so high pressure / vacuum, high pressure erosion, or high temperature erosion, corrosion, Explosiveness, they're very versatile in how they can be designed, and typically there's no product contamination in the scrubber. At this point, I'll pass it over to Jared. He'll go through some process installations.
Thanks so much, Craig. And if you guys are still out there awake, and we're going to move through this kind of quick. So I just want to give you guys some real-world examples of how these scrubbers will look at installations and applications. So first one up here, we've got an image of a large, these are for an odor control, and this is going to be looked at as a municipal application. What we can see here, these are round vessels, as Craig discussed, and we can see an integral stack on top of them and centrifugal fan to the base at the bottom. This is a 99% removal of H2S. Next, we do have a outside location. This is for a chemical manufacturing for HCl scrubber. This is also at about 95% removal. We can see this has an integral fan to the scrubber itself. It is a vertical fiberglass as well. Next one here we can see is an aerospace for metal plating. This is another fiberglass scrubber vertical outside. This unit does have a centrifugal fan located at grade. You can see the ducting right over to it. This is located outside for more floor space inside. Next, we can see a rooftop installation of an 8,000 CFM ammonia scrubber for semiconductor application. Another semiconductor application for a scrubber. And in this image, we can see redundant pumps and also redundant fans, which is a common call we see on this type application. And just quickly wanted to touch on this one of our products here, which is one of our applications here, biofilter. This unit does operate off of a biological principle, and we do mainly see applications with HAPS and VOC, and this does operate off of using a bacteria and a fungi. We can see this to the right. You can see an image of this process taking place, and this is actually an image of a biofilter. Another great example we have of a unit here, we can see some of the material that is used. This is the media that does have the bacteria and the fungi that does live in this media. And we have another example of a hex chrome application. This is a very complex application, and we see a system that's been specially designed that can remove the hex chrome or hexavalent chrome from the airflow. And the last example we'll show today is of a NOx scrubber. This is used at an application for pickling and passivation line with stainless steel. This is a complex process that does take multiple towers with multiple different techniques to remove the NO and NO2. In this particular example, we did have other contaminants in the airstream. Thank you guys for your time.
Thank you, Craig and Jarrett. Really appreciate that. We just want to be respectful of everyone's time. We understand we're going a little long here. So just a reminder to everybody, we'll do one quick question, but if we don't get to your question, we will get back to you individually. Don't worry, we always get back to all the questions. So one way or another, you will hear from us. And just a reminder, on the right or on the left-hand side, typically, is your resources section. There's a couple things there for you, including the wet scrubber summary that can help you out with the quiz. There are also copies, PDF, of the slides for today's presentation, as well as a couple of other items. So feel free to download any of the items and print them out, save them, whatever works for you. So as long as you have fulfilled the 50 minutes and the 8 out of 10 questions, you will have the ability to print out a certificate. So once you've done both, that little pop-up screen is going to show up for you, and that's where you will print your certificate. We're going to go quiet after the question here, but the actual platform itself will remain live for about 30 minutes to give everyone a chance to finish up the quiz, finish downloading any types of materials that they need as well. So we're going to do one quick question here, and I just want to thank all of you for coming. Appreciate you being here, and let's pick one quick one here and get it out.